Welcome to yet another class. I'm Dr. B, your science teacher online, and today we are going to be discussing nothing other than determination of internal energy. Now, how do we calculate internal energy? In a very simple way. Now, do not forget that this is Dr. B Science Classes. You owe me a duty to simply subscribe to this class. Now all you just need to do is go to the subscription button and click on the bell and select all, and that is all. You also need to share this class with your friends, share it with those in engineering department, those in chemistry, physics, even mathematics. Alright, now tell them to subscribe. Subscription to this class is free. You don't need to pay anything. And then when they subscribe, they simply can leave a comment, or they can even leave questions in form of comments, or even a like, as the case may be. Alright, even on Facebook is also Dr. B Science Classes. And all they need to do is just to click on the tap on the follow button, and then they can also leave a comment. So whenever these videos come up, they will have them free. Thank you. Now, we are going to be talking about determination of internal energy. The last class we had, okay, we tried to look at the differences between internal energy and enthalpy of a reaction. We said that these two terms can be, they are interchangeable. People use them interchangeably, and they do not bother the fact that these very two terms are, gives different results at the end of a particular reaction. We had discussed exhaustively on that. Okay, so we made ourselves to understand that when you talk about enthalpy of a reaction, you are talking specifically about changes in heat, that is, heat changes with respect to constancy in pressure. And when you talk about internal energy, you are talking about heat changes at constant volume. And that heat changes at constant volume usually is always what will give rise to work done. And it is experienced especially in systems that are mostly open system, where there is an interchangeable process between material and energy. Okay, now today we are going to look at how we can possibly calculate internal energy. We are given this particular kind of a chemical reaction where zinc reacts with sulfuric acid to give you zinc sulfate and hydrogen gas given off. I want us to know that this reaction can take place. You can measure internal energy in this reaction and also measure enthalpy in this same reaction, but you are going to have separate results, even though both of them are known to be state function, and both of them are also known to have much to do with changes in heat. But know that the results you obtain for enthalpy will be results that are obtained at constant pressure and will be different from the one you obtain for internal energy at constant volume. Okay, now when we want to determine internal energy, we are looking at system of a reaction where reactions are operated at constant volume. And at this point in time, we will quickly reflect our minds, or take our minds back to what we have done earlier in this class, trying to look at the relationship between enthalpy and internal energy. Now I want us to know that the relationship between enthalpy and internal energy is written as delta H is equals to delta U plus change in N, R, and T. This is the equation that we had derived some time ago in this class concerning the relationship, or pertaining to the relationship between enthalpy and the internal energy. Now remember that we said they are closely related, but they are not the same. So we can quickly use this equation to calculate for internal energy in this kind of reaction. Remember that our interest is on gases. We have said before that usually internal energy and enthalpy are mostly being carried out at processes that involve gases, more than processes that involve liquid and solid. Now, typically looking at this particular equation that we have here, we are interested in a process that has to do with constant volume. And with constant volume, we are talking about gases. Okay, now the change in enthalpy is given to us at the end of this this equation, which is minus 151 kilojoule per mole. So we have here minus 151 kilojoule per mole being equals to delta U, which is change in internal energy, that particular factor we are looking for, plus, now this is change in N, and N is the number of moles of gases. Now if you take a look at this question, you see that it is only one gas that we have here, and that gas is hydrogen. Now if you see that at the product side, it is only hydrogen gas that is being given off. Therefore, we are dealing with hydrogen. And the hydrogen in this equation is only 1 mole. It is only 1 mole of hydrogen that is being given off in the course of this reaction at the product of this particular chemical reaction. That means that the change in N is just 1, because it's only 1 mole of hydrogen gas, which is what we are considering that is released at the end of the chemical reaction. Therefore, the change in N will be 1 times Ru and T are basically constants. So Ru is the gas constant. So gas constant is 8.314 per Kelvin per mole. And then we multiply this by the standard temperature. And standard temperature is 298 Kelvin. Now this is how we will get those values to substitute in this equation, which serves as a equation of relationship between enthalpy and the internal energy, for us to be able to solve the internal energy problem. Okay, so now with this, it is simple. What we will now have is minus 151 kilojoule per mole is equals to delta U, which is the change in enthalpy, now plus. Now if you multiply 1 times this, you are going to get a number, and that number you are going to get is minus 2.5 kilojoule per mole. Okay, so when you multiply this by this, you have minus 2.5 kilojoule per mole. Now this you have obtained for change in N number of moles with respect to the gas constant and the standard temperature. So you can now easily sort out this. Now this will still give you minus 151 kilojoule per mole equals to change in internal energy. This times this will give you minus 2.5 kilojoule per mole. Now making this the subject of your formula, we'll have that delta U is equals to minus 151 kilojoule per mole. And this will move to this side, which is plus 2.5 kilojoule per mole. Okay. Okay, so we have this value. Okay, sorry, I think we have a slight issue here, and the slight issue we have here is that this is positive. All of them here are positive, so we don't have a negative sign. All right, so we have to take note of that. So we don't have a negative sign, so it is actually this plus that. So it is when you now have positive sign here too. Okay, so by the time you now move this to this side, it will give you a negative sign, which is minus. Okay, so delta U, which is change in internal energy, will now be minus 151 kilojoule per mole minus 2.5 kilojoule per mole. Remember that minus minus is plus, and we take the sign that belongs to the larger number. So this plus this will rather give us minus 153.5 kilojoule per mole. Okay, so this now becomes your internal energy for this very equation. Now, what does this mean? This means that the 2.5 kilojoule per mole that you obtain from this is actually the amount of it's actually the work done in this particular reaction. Yeah, is the work done in this particular reaction. That means that the internal energy which this particular reaction had or possessed in order to perform work is minus 153.5, but the work done itself that has been performed out of this internal energy is 2.5 kilojoule per mole. Now this is quite obvious because it's a negative sign that you have gotten here, which means that the work that is done is actually the work that the system gains energy. Alright, so the system gains more of internal energy, and that is why the delta U is negative. That is the same thing when you say the delta H is negative. I always said that delta U, which is internal energy, and delta H are related, except that one of them has to do with heat changes when pressure is constant, that is entropy, and one has to do with heat energy when volume is constant, that is internal energy. Okay, so the results you get at the end of the day will differ slightly, but one complements the other, and that is why we had said here that this is more of enthalpy, telling you the work that is done by the system when this amount of internal energy is supplied in this particular chemical reaction. Now, this is how simple it is for you to calculate internal energy for a chemical reaction and be able to relate it with delta H, which is the heat change at constant pressure where work is not actually done. Okay, so with this, I'm very much sure that you can solve more problems that has to do with internal energy. Join us in our next class to see the much that we are going to also do in thermodynamics and probably in other aspects of chemistry and physics alongside mathematics. I still remain your Dr. B Science Classes. Go there, Facebook, go there too both on Facebook and YouTube, and simply subscribe and share. Until next time, I remain your science teacher online. It's bye for now.